Uh-oh. Okay, so we're going to cover related rates. So probably the quickest way to start would be to give an example. So let's say, for example, we know that the volume of a cone is equal to pi over 3 radius squared times the height. Yep, clean that 3 up a little bit. Okay, so let's say just out the blue you had a cone, and that cone was filled all the way to the top with water. Okay, so to find the volume of the water in that cone, you know you had to look at your radius, and you had to look at your height. So let's say you had water leaking out of it. And after an unknown amount of time, that very same cone now has dropped a little bit. At least the amount of water has dropped a little bit. Okay. But now this is your radius of the amount of water in there. And this is your height. Okay, so let's say it keeps on going, and let's say that very same cone drops down to very little water left in it. Okay, so now this would be your radius, and that would be your height. So this is really just another way of saying that the volume is a function of two variables, where you have your radius and you have your height, at least this particular one. Okay, so the volume of a cone is a function of two variables. Okay, so let's say if we tried to figure out, okay, exactly what is the rate of change if we had to find it for a cone. Okay, so we get this formula and we just differentiate both sides. With respect to time. Okay, because we just don't know exactly how much time passed, but we do know that time did pass. Okay, so the rate of change of the volume with respect to time is going to equal, actually, let me just factor out the pi over 3 now, times the derivative with respect to time of the radius squared times the height. Okay, now since we know these aren't just constants, because if they were constants, we'd bring them out to the front. Since we know they are variables, we use the product rule. Okay, so that's going to equal pi over 3. So you have the first times the derivative of the second, so r squared times the derivative with respect to t of h, plus the second times the derivative of the first. Okay, so using implicit differentiation, you have r squared times the derivative of h with respect to t, plus the height times the derivative of r squared with respect to t. Remember, we bring our 2 down to the front, and we multiply it by dr dt. Oh. All right. And really from there, if you just wanted to kind of clean it up a little bit, you could. So you have r squared, the rate of change of the height with respect to time, plus 2 times the radius times the height times the rate of change of the radius with respect to time. Okay. So this would be the formula for this particular volume. Well, not formula, derivative for this particular formula. Okay. It depends on what shape you're starting with, exactly what you're measuring, what you're given. That kind of dictates what your actual formula will look like. All right, and I'll give you a couple of examples. Bring that down a little bit. Oh, the original is the volume of a cone. All right, so let's say we're starting off with okay, so let's say suppose x and y are both differentiable functions of t. And are related by the equation y equals x squared plus 3. And let's say if we want to find dy dt when x is equal to 1. Ooh, that's a little bit. Just gonna straighten that up some. Oh, sorry, left out one last part. Given that dx dt is equal to 2. Oh, clean that up a little. All right, so really this is just taking the implicit differentiation from last class and moving a little bit more with it. Okay. So we know we're given x equals 1 and dx dt is equal to 2. And we have to find dy dt. Okay, so we just differentiate both sides. Derivative with respect to t of x squared plus the derivative with respect to t of 3. Okay, so it really doesn't matter as far as when you differentiate a constant. If you're differentiating with respect to any variable at all, it's going to be 0. So whether it's t or x or anything else, it's going to be 0. So this just becomes 0. Okay, so you have your dy dt equals derivative of x squared with respect to t. Going to bring down your 2. Subtract 1 times your dx dt. Okay. Then once you have that, you just plug in everything that you were given. Okay, so we know that's going to equal 2 times your x equal to 1 times your dx dt is equal to 2. So it's just going to equal 4. Okay, so really that's just your rate of change of y with respect to time.
Was that the difference between when everything was d to dt, then it was, and then you took the derivative of all that?
Yes. Yeah. All right. So any questions on this one? All right. Leave that up for, lower that down a little bit. Leave that up for a few seconds.
Where did we get? Oh, never mind.
Oh, you got it?
Yep.
Oh, okay. All right. Okay, so let's say we apply this to an actual problem. Let's say, for example, if you have air is being pumped into a spherical balloon. I don't know why I said cylindrical. At a rate of 4.5 cubic feet per minute. Or you can make it 9/2. Yep, there's that. So 4.5 also equals 9/2. Okay, find the rate of change of the radius when the radius is 2 feet. Clean that W up a little. Okay, so you know when you see spherical balloon, it's basically telling you a perfectly round balloon. So we know that spherical balloon volume is equal to 4/3 pi radius cubed, which is the volume of a sphere. Okay, so now we need to go over what exactly we're given. Okay, so we know that air is being pumped in at a rate of 4.5 or 9 divided by 2 cubic feet per minute. So that means the volume is growing at that rate. So the rate of change of the volume with respect to time is equal to 4.5 cubic feet. Or cubic feet, I might as well write it as cubic feet per minute. Okay, so we know that's the rate that the volume is changing. Okay. So we also know that we're going to look for the rate of change of the radius when the volume is, when the radius is 2 feet. So the radius is 2 feet. Just means that we're given that R is equal to 2.
How come the rate of the air being pumped into the balloon is equal to the derivative of time? So you're saying that dV/dt
Yes.
is equal to 4.5 cubic feet a minute?
Yep, because we know that since air is being pumped in at that rate,
Oh.
that's the rate that the
The
volume.
rate of change.
Yep, the rate of change of the
Okay.
volume.
Gotcha.
Oh, do you have a question? Or? Oh. All right. So we now, from there, we just find the derivative of both sides of our formula. So the rate of change of the volume with respect to time is equal to 4/3 pi times the derivative for the radius cubed. Okay. So that means our derivative of our volume with respect to time is equal to 4/3 pi. Bring down our 3. Subtract 1 times derivative of the rate with respect to time. Okay, so here the 3's cancel out. So the rate of change of the volume with respect to time is equal to 4 pi radius squared times dr dt. Actually, if you look at the last line, they want to find the rate of change of the radius, which means you're solving for your rate of change of the radius. Okay, so that's what you're solving for. So really, you can just plug in everything here, or you can get it by itself and plug in everything. It's completely up to you. So the rate of change of the volume with respect to time, we know that's 9/2, or 4.5, whichever one you want to use, equal to 4 times pi. We want to know when the radius is equal to 2, so we make that 2 squared times our dr dt. Okay, so if we go ahead and plug that in, we can make that 4 times 4, which is 16, and divide both sides by 16 pi. Okay, so from there, our rate of change of the radius with respect to time is equal to 9/32 pi, which is your exact answer. Or if you plug that into your calculator, you'd end up with 0.0895. Squared feet per, was it minute? Yep, minute. Feet per minute, sorry about that.
Sorry, I missed that.
Which
Why
part?
were we dividing it by 16 pi?
Oh, because I just 2 squared is 4. 4 times 4 is 16. So just solving for the DRTT.
Gotcha.
So let me make a little note of that. Four pi 2 squared equals 16 pi. So hopefully I won't confuse anyone else. All right, any questions on this one? All right, leave that up for a few seconds. All right, so let's get another example. Okay, so let's say a box with, well, let's say it has a width. I don't want to have width in there too many times. Has a width of 12 centimeters and a length of 9 centimeters. Okay, the volume of the box is decreasing at a rate of 541 cubic centimeters per second. With the width and length being held constant. Okay, so what is the rate of change of the height? In centimeters per second when the height is 6 centimeters.
Is it just centimeters per second or centimeters cubed?
For the,
Rate of change?
this one?
Yeah.
Yep, just centimeters per second. Remember, that's just your rate of change. So that's like your speed.
Oh.
Okay. So we know that the volume of a box is equal to length times width times height. Okay. So now we look at exactly what we're given. Okay. So we know the width and the length are constant. Okay. We also know that the volume is decreasing at a rate of 541 cubic centimeters. Let's say the volume is decreasing. Okay. So that means since the volume is decreasing, our rate of change of the volume with respect to time is actually equal to negative 541. So decreasing just means negative. Okay, so now that we have an idea of what all of our given factors are, we just have to differentiate both sides. Okay, so rate of change of volume with respect to time is equal to length and width are constants, so you can bring those right on out. This way you won't have to go through the trouble of differentiating three factors. So remember, those are constant. Oh, actually, we did have one more given, but I'll do that on the side here. Okay, so one more given. Where was it? The length and width are being held constant, so that pretty much lets you know that they don't change at all. Okay, so if let's say we didn't decide to factor those out, we would end up with a dl dt and a dw dt, but the dw dt and dl dt would be zero because they don't increase or decrease, they're held constant. So that's why you can go ahead and just factor those out from the beginning. You don't have to worry about them. So even if you did forget to factor them out, it would just be zero. So you wouldn't have to worry about them. Okay, so this is times derivative with respect to t of h. Okay. So we know that our volume is decreasing at a rate of negative 541. So negative 541 times our length and width, might as well say 9 and 12. Plug those in there. Times dh dt, which is exactly what we're solving for, the rate of change of the height. Okay. Now the fact that the height is equal to 6, it really doesn't mean much in this particular one, because we already know you just need our rate of change of the height. Okay, so the rate of change of the height would be the same no matter what. Because if you remember, where is it? Yep, we're solving for our dh dt. Oh, we're at 29. Let me hurry up. Okay, so that's going to equal negative 541 times 12 and 9 is 108 dh dt. So we just divide both sides by 108. Our rate of change of the height with respect to time is equal to negative 541 over 108. And we'll leave it as an exact answer.